like to thank the organizers, and it's really a pleasure for me to be here in this meeting to honor Eduardo. That's a person for whom I have a great admiration, not only as a scientist, but as a person also, having the possibility that I had to live you, not to be your friend for so many years. So this is what I'm going to talk, and these are the peoples the persons involved in this. I'm going to. So these are their pictures, and that's me many years ago. Fernanda. And these are the guys, they are all from Rio de Janeiro. And that's the people I've been working with. So perhaps this is the starting point of many talks about topological systems, but I could not avoid talking about this. And there is this normal search that for this Majorana, and they should appear in this P-wave superconducting chains, but they are rare in nature, so there have been several tricks to try to simulate these P-wave superconductors. Superconductors using semiconductors, playing with spin orbit and magnetic field, and but they are really hard to obtain. As far as I know, never anyone observed a Majorana fermion so far. So what I'm going to talk is about another class of topological systems, which are probably the simplest topological materials in nature, which are these topological insulating chains. And these chains, they are very interesting. Also, they present topological phases with edge excitations, which are protected by several kinds of symmetry. And they have a basic difference with the Kitaev model, or with the Majorana on the edges, but they really look like very interesting systems as well. So I'm going to concentrate here in these SP hybridized chains, but in fact, you can map these hybridized chains in more commonly known SSH, and here everybody knows the SSH, and RM is for Rice-Millet, that generalized somehow the SSH chains. I'll show this. So the SP chain, that's the one I'm going to concentrate it. I think for sure it's the easiest model of a topological insulator. It's really, there are two bands, an S and P band, let's say. That's nice because I'm not going to consider interactions, so it's good that I have wide bands, S and P bands. And then there is a hybridization term between these two bands. The important, the fundamental thing here is that I'm mixing orbitals which have an orbital moment that differs by an odd number. So this hybridization here, it's actually antisymmetric when you have hybridization in neighboring sites. Vji is minus Vij. So this is the basic ingredient that makes, that confers topological properties to these chains here. So it's this antisymmetric hybridization, which is essentially the basic, is the feature which provides the non-trivial topological quantities. And this model here, as we can see, we can show, it has a topological phase transition when epsilon over 2t is equal to 1. So when this quantity here is less than 1, there is a non-trivial topological phase with edge modes. And when this quantity is larger than 1, then you have a trivial phase. So there is a topological phase transition here, which is, and these phases are distinguished by these indexes, winding number, Schur numbers, whatever you calculate. No? Now, with my background, so here is the, let me show you. These are the bonds are the poles of this equation here. You see that the hybridization, which is antisymmetric, it enters with this sign K here, no? Very similar to the P-wave interaction in the superconductor. No? And this is the source of all non-triviality. No? So you can close a gap varying these parameters here, and you have this band inversion as you have in the spin orbit case, but here the spins are always the same. No? You don't have spin flip with the hybridization. So in this sense, it's very different from the spin orbit case. And this is the wave function of the edge modes in the topological phase. You see that they are well there sitting on the ends of the chain very well. For someone that has a background on quantum phase transitions, like in my case, I cannot avoid to think which is the nature of this topological phase transition. If you look naively at, well, you have -1 and +1 in the trivial and topological phase, so this is could be an order parameter, something like this winding number, and then this would suggest that you have a first order phase transition, something like that. But that's really not the case. No? But if you think naively, you think that this would be a first order phase transition, but that's not really the case. It's quite clear. No? But if it's really a second order phase transition, what you need is to find a diverging length. We all studied in statistical mechanics, now when you study phase transitions, in order to be able to speak about scale invariance, use scaling, everything, you need to have a single length scale in your problem that's going to diverge at the quantum critical point and is going to make the system scale invariant. So it's essential to have this diverging length in the problem to be able to speak about a topology, phase transition in general. No? So it was nice we could really identify which is this diverging length. And this diverging length is nothing else than the penetration depth of the edge modes inside the bulk of the chain. So we can vary the control parameter, epsilon over 2t, and we can approach the phase transition, and we can measure the penetration depth of the edge modes inside the chain, and we see that indeed when this is at the quantum critical point, this thing here diverges, so this is the diverging length associated with this phase transition. I call it the quantum phase transition because it's a phase transition that occurs at t equals 0. No? And then we can give a description of this type of phase transitions, even in the absence of another parameter. We don't need really to define, to get another parameter to be able to identify the universality class and all the things about this phase transition. Well, one thing that we can identify immediately is the dynamic exponent associated with that. And this arises trivially from the linear cross of the modes at the topological transition. So we can identify the dynamic exponent as being z equal 1. And the correlation length, in fact, we can obtain from the simulations, and nu turns out to be equal to 1 also for these chains. No, length scale for me here is, it could be, but it's not that. I measure the penetration depth of the edge modes, how the wave function goes into the gap is really nu z. It's not just the penetration. Here I get only nu. If I measure the gap, I will get the combination nu z.
All right, thank you. Well, going back to the same question about the mass, I think that since you have two bands, the P and the S, I think you have two species of the Dirac fermions. And then the topological transition is when the mass change sign.
Yeah, but that's the same thing here. It's when the mass vanishes.
Yeah, so when the mass vanishes, the correlation length, because that scale sets the spread of the zero mode wave function. So these two things are one and the same, is that when the mass goes through zero, the correlation length diverges and then you connect them. The decay of the zero mode wave function is controlled by the mass.
As I answered to him, the mass is the gap, and the gap is nu z. What controls the vanish of the gap is the combination of the dynamic exponent and the correlation length exponent. Here, because both are equal to 1, in fact, the mass, the gap goes inversely with the correlation length. So, no, both sides. On both sides. This has an unpleasant feature that I can only define that from the topological side, because in the other side I don't have edge modes. But Wei Chen has other proposals to generalize that coming from the trivial side also, because here I can have only that coming from the non-trivial side. So I can obtain the universality class of this thing, nu z. I can get the product nu z. I can get that, and I can even calculate the ground state energy, the divergence of the ground state energy at the divergence, the critical behavior of the ground state energy as a function of nu, and I get this expression here. This is related, this delta square log delta. Delta is the gap that's going to vanish. This is associated with alpha equals 0, the exponent for the free energy. And then you see that these exponents satisfy this quantum hyperscaling relation here with alpha equals 0, d equal 1. This would give a compressibility. If delta depends on the chemical potential, this would give the behavior of the compressibility at the topological transition. Then we have this thing here working well. Of course, this raises important questions. Is there an upper critical dimension for topological transitions? Are there mean field exponents? So these are other questions that arise here on this. So going back to the SP chain, I want to see what is the nature of these edge modes in this chain. And then I follow the nice for me that was a Bible for some time, the review by Ali Chair. and I see how you move to Majorana operators. Then I try to write this SP Hamiltonian in terms of these Majorana operators. I have to do 2 transformations because I didn't know the Bogolyubov transformation yet. And then I get this Hamiltonian here, which is the which is the SP Hamiltonian written in terms of Majorana. And then we do this trick, like we put V equal T, we put epsilon equals 0, which means that we are inside the topological phase, and we get this simplified Hamiltonian here. And looking at this Hamiltonian, we see that there are 4 Majoranas which are missing in this Hamiltonian here. No? So you have 4 Majoranas that are missing, and that's difference from Kitaev. Now, Kitaev has 2 Majoranas missing in this thing. So we have, in fact, 2 Majoranas on each edge of the chain, and you can combine these Majoranas in a fermion, and what you get is a funny fermion, which is a mixed electron with SP components in it. So this is the nature of the edge modes. No? They are not Majoranas, they are 2, it's a funny fermion, no? With SP character. Well, an additional motivation to study these chains is this phase diagram here of carbon. No? Carbon, it has the 3-dimensional form, no? Which is diamond, well known and well valued. There is the 2-dimensional form of carbon, the famous graphene, graphite, but there is also a 1-dimensional form of carbon that is less known, but that's when the hybridization is SP. This type of hybridization tries to give rise to chains of carbon atoms. So these systems have begun to be studied recently, and they are exactly a realization of these SP chains as we are discussing here. So now the idea was to study the properties, the transport properties of the SP chains. But here, instead of adopting a direct calculation of an SP chain, we use a trick to obtain the properties of the chains. That's essentially to build a single electron transistor and couple 2 semi-infinite SP chains on each side of a quantum dot. No? And then we are going to calculate the thermoelectric properties of this kind of transistor, apply a very small voltage between the 2 sides, between the 2 insulators, so that we can use some equilibrium situation. We can consider this is an equilibrium situation. Well, so this is the kind of system that we studied. Attaching in each side of the quantum dot 2 Suhl-Schrieffer or Rice-Meillez chains, which, as I mentioned, can be mapped into the 2 types of SP chains. One SP chain where the hybridization is intratomic, that one maps in the Rice-Meillez, and the one that the hybridization is intersite, that maps in the SSH. So for simplicity, we work with these 2 type of chains here. So we start with the more difficult one, that is the Rice-Meillez. And the Rice-Meillez is that maps in the diatomic SP chain, is essentially a SSH chain where you have alternating bonds, but here you have also some on-site energy that varies from epsilon to minus epsilon, just to simplify things from one side to the other one. So this Rice-Meillet chain also has been studied a lot for topological excitation, solitons, and it's well known it has a topological phase transition. In the case of the SSH, with epsilon equals 0, it has a topological phase transition. When V1 is smaller than V2, then you have this you have a topological transition with one trivial phase for V1, one topological phase for V1 smaller than V2, and a trivial phase in the otherwise. To obtain these thermoelectric properties of this device, the transistor and the chains, what we need to do is to calculate the Green's function of the quantum dot connected to the semi-infinite chains. And for that, there is it's a well-known technique. So GD is the Green's function of the quantum dot, and small gd is the Green's function of the dot itself. And this comes from the fact that I have attached two semi-infinite chains to each side of the dot. For some reason, I have an exclamation point on the place of omega. So this is an omega. So I can calculate this. It's not complicated. And what the functions that are important here is the real part of the Green's function of the semi-infinite chain at the point that connects to the dot. This TD is just reminding, the TD is the the TD is this coupling here between the dot and the chains. So we can calculate that. Wow, this is bad. It's really bad. Well, I have a PDF version of this thing here. I don't know if it's bad. So there is a very useful and standard technique to obtain all the thermoelectric properties of this system. So what you have to calculate is a T matrix, and the imaginary part of this T matrix will give the lifetime of the quasi-particles inside the quantum dot. And from that T matrix, then you can calculate the thermal conductivity, you can calculate the thermal power, you can calculate the Widman-Franz ratio, and you can calculate this thermal power. This is related to the power factor that Teresa spoke in the first day. So what we need indeed is to obtain that G naught, and then from that we can obtain all the thermoelectric coefficients of the problem. So the point now is to obtain the dot, the wave function of the edge modes, the Green's function of the edge modes that connect to the dot. Now it's a semi-infinite chain, and then we can go to some very old and nice material. Michael Thorpe, he disappeared. I knew him very well, but he don't know where he is now. But he worked a lot with these one-dimensional systems and tried to obtain density of states. He was a specialist in Bethe lattice that was very famous at some point in physics. And then we can calculate the Green's function, the edge Green's function, using this thing. It's very easy. It's a non-interacting problem. You can do an exact calculation, and you can calculate then the Green's function. And from the imaginary part of this Green's function, you obtain the density of states at the edge of the SSH or the Rice-Meillez chain. And this has a very interesting shape. Here's the density of states. There is a delta function which is related to the edge mode, and there is a dispersing part here. But the weight of the delta function is very nice because it's really this D, which is related to the distance to the quantum phase transition. So it's D plus modulus of D. So when this is smaller than 1, we are inside the topological phase. You add these two things and you get a factor 1 here. But when we are outside the topological phase, this thing is negative, and then this factor cancels, and the delta function disappears. So this Green's function, let's say it's a topological marker in the sense that it can distinguish when we are in the trivial or when we are in the topological phase of the system. So we need the real part also of the Green's function to be able to calculate the dot Green's function. And here is the edge Green's function, actually the edge density of states in the 3 phases of the system. In the trivial phase, there is a gap, and these bands here, below and above the zero energy or the chemical potential. In the non-trivial phase, there is the same bands, but there is a delta function here at zero energy, which is just the weight of the edge mode. And this is the real part of the Green's function that we are going to need to calculate also the thermoelectric properties. For the Rice-Meillez, we can also obtain that. That's really rather different, no? And here we are always putting the chemical potential at the energy of the quantum dot so that we can simplify the things. So, but then we can obtain everything exact without not much work, no? And then we can we'll present the results now from calculating these things here. First, in the SSH model, we can calculate the conductance in this device. No? And here it's in the trivial, topological, and at the quantum phase transition. At the trivial and topological phases, the conductance is always thermally activated because the shades are insulating. No? So there is some reflection in these quantities from the presence of the edge of the delta function in the non-trivial phase. So although there is this gap in the density of states, no? But in the non-trivial phase, there is this delta function. It doesn't provide any conductance, no, to the system because the bulk is insulating, but it affects a bit the conductance in the phase. There is a distinction between the two conductors in the trivial and non-trivial phase in spite of the gap that you need to excite to give rise to conduction. And this one here is the conductance at the topological phase transition. Now the system becomes a metal, no? Because you have, it's a Dirac metal, no? You are just at the crossing point of the system, but they are able to, system as a whole, no? There is a current that can go through the device, and this conductance is really quantized and goes to 1, the quantum of conductance here as we can see here. You can also calculate the thermal conductivity. You can calculate the Widman-Franz ratio for the SSH model. And you cannot calculate the thermal power because the thermal power is zero because there is particle-hole symmetry, and the thermal power is zero in this SSH chain. And then we go to the Rice-Meillet chain, and then something nice occurs. The Rice-Meillet chain, because there is a finite on-site energy, it breaks the chiral symmetry of the SSH chain. And when you calculate the conductance, and this comes out from the calculation, you see that it goes to a factor 1/2, to a value 1/2, instead of the value of 1 that had appearing in the SSH model. And when you decrease this on-site energy, that is, when you move towards the SSH model, you see there's this funny behavior. In the SSH, the conductance was 1. Remember, it was quantized to 1. But here, when you get epsilon small, approaching 0, you start from the Rice-Meillet, but then it goes up as if there is some combination of these two E/2 charge in the material. So this is the conductance now in the two situations, at the quantum phase transition and in the trivial and non-trivial phases. Again, it's thermally activated because the bulk are insulating in these systems. And finally, I can now, in the case of the Rice-Meillet, calculate the thermal power in this material. And when we calculate the thermal power, it's not really a difficult thing because you have everything analytically, almost we can put inside an integral. And we get something very funny, that the thermal power, instead of going to 0 as would be expected for a Fermi, for some, as would be expected from the third law of the thermodynamics, because the thermal power is really related to the entropy by this Kelvin formula here. Instead of going to 0, it goes to saturates at a funny value here that we didn't have any idea what would this satisfy. We could initially understand why it doesn't go to the usual 0 value expected for a metal, or a semi-metal, or a Dirac metal. And we saw that could be traced to some singularity at the free energy of the system, and that we could understand. But then we could not understand exactly what was this value here for the thermal power, until we came through some very old papers by, here it's unfortunate I didn't cite, but I think it's Scheitkin. He has a very nice interpretation of the thermal power. That is, essentially the thermal power is the entropy per carrier divided by an effective charge of the carriers. So what we did here is assume that, let's suppose we have a log 2, the ground state is degenerate, it's twofold degenerate, and then if we use the charge as appeared from the electroconductance plus or 1/2, and then we divide this thing, we get exactly this value here. No? So this is like a universal value that depends, comes from this nice expression here that connects somehow thermodynamics and transport properties. No? And so we get this nice result for the thermal power here. And then finally, these are the other quantities calculated for the Rice-Meillet, and nothing really very special. So that's it. I don't know. You are already standing here. Sorry.
Mu-Hsu, thanks for this very nice talk. I'm particularly interested in your hyperscaling law. How do you derive it exactly?
Well, I cannot derive it now, but it comes from the fact that when you have a quantum phase transition, you don't have temperature. In normal phase transition, you scale the free energy over kT to obtain something that is dimensionless, and you scale by kT and L to the power D. You divide this to make an invariant. Here we don't have kT to divide, so you have to introduce a characteristic energy scale, when this energy scale is just the parameter that controls the quantum phase transition and how it scales at the quantum critical point. For example, in Kondo lattice, it would be the Kondo coupling, for example, and this Kondo energy scales like J to the minus Z. No, J to the minus Y, let's say, and then this Y is the one that enters into the hyperscaling. And then, because energy is connected to time fluctuation, using the Heisenberg principle, you can identify Y with Z.
But this is an assumption, no?
No, this is not an assumption. It gives the results that are completely well known and used everywhere in the world.
And also, I noticed that your specific heat exponent is 0.
No, it's not in a specific heat.
Okay.
The alpha is defined by the singularity of the free energy, not specific heat, because, of course, at T equals 0, you don't have this interpretation.
But then it's a constant, right? So alpha equals 0 means it's a constant.
Yeah, alpha equals 0 means it's a constant. No, the free energy is delta square log delta. So it's delta square, which would be the mean field, no? Alpha equals 0. But then, in fact, here we have this log delta, perhaps because we are at the upper critical dimension of the topological transition in this case.
Okay, I see. Thanks.
Other questions? Yes.
Just a quick comment to the question was raised earlier about whether you can define this length scale for both sides. There is actually a very trivial way to do it. What you need to do is to add an imaginary momentum. You extend, you analytically continue your entire problem with one more imaginary momentum. Then, on both sides, when you open the gap, your branch point, where these two branches meet, will move to an imaginary axis. And that momentum, whose inverse is exactly the length scale you're after. So what you define as the quote-unquote divergent correlation length is basically the inverse of that imaginary momentum, which exists in both cases. So you can actually rigorously discuss, and you should be able to show very easily that they have exactly the same exponent. Yeah, so there is a simple answer to that question.
You mentioned this thing about the upper critical dimension and hyperscaling, and I find it very hard to disentangle from this argument what depends on the existence of a Landau theory based on an order parameter, what doesn't. Because, of course, we know that a topological phase transition cannot be written as a Landau theory. So does it make sense to talk about an upper critical dimension in that case?
All you need to have is the old renormalization group. What you need is an unstable fixed point that is going to separate the trivial from the non-trivial phase. When you have an unstable fixed point there, then you can construct a whole scaling approach close to this quantum to this fixed point. Then you can write an expression for the free energy. You can introduce all the exponents. And actually, you don't need any other parameter to characterize.
How do you do the RG? How does the RG know the system is ordered or disordered or whatever?
It's an old paper. that I have done
but
this.
If the phase transition does not involve a local order parameter, but it involves
No, the RG
global
distinguishes the two phases very easily, because the trivial phases go to a strong coupling fixed point, and the trivial phase, and that's in fact the trivial phase in the Kitaev model is just the Bose-Einstein condensation fixed point, where the pairs are strongly coupled. So you see from the renormalization group that the flow of the trivial phase is to this strong coupling fixed point, and the other phase, in fact, goes to a chaotic attractor in this case. So you can distinguish from the flow of the RG, you can see the nature of the two phases. The topological phase, there is nothing real. It's chaotic, but the chaotic is not a privilege of being due to the topology. But the trivial phase you can identify from the flow to the strong coupling, where the pairs are really tight, and you are in this trivial phase of the Kitaev model.
Okay. We have to talk about it.
You absolutely will see a different fixed point. It's one-dimensional. You have two fixed points, right?
No, I have three fixed points.
Three? Oh, one unstable.
I have one unstable and two stable.
Sure. This has nothing to do with phase transition. It's just any partial differential equation has.
No, that's the heart of phase transition.
I know, but I'm saying that this is much more general. It doesn't require phase.
Yeah, that's the RG, the view of a phase transition.
Do we have more questions? I think we had plenty, so thank you so much. And thank you.